Okay, welcome back. So last class we talked about discrete random variables and discrete probability distributions. This class we're going to talk about continuous random variables and continuous probability density functions. You already are aware that a discrete random variable can take on clearly separated values and is the result of a count, and a continuous random variable can take on an infinite amount of values within a given domain and is usually the result of a measure. Okay, let's get started. So first we will take a brief look at a uniform density function, but most of the time today is going to be spent looking at the normal distribution and properties of a normal distribution. Okay, objectives for today. Use the uniform probability distribution, graph a normal curve, state the properties of the normal curve, and explain the role of area in the normal density function. Let's get started using it. For starters, the uniform one. I'll read the problem to you. Suppose the UPS service, United Parcel Service, is supposed to deliver a package to your front door, and the arrival time is somewhere. Let me change the color on my pen here. And the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m., the time from 10 a.m. when the delivery is supposed to take place. That is, the delivery could be at 10 a.m., x equals 0, or at 11 a.m., x equals 60, with all 1 minute interval of times between 0 and 60 equally likely. That is to say, your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. So, with all those 1 minute intervals equally likely. The random variable x can be any value in the interval from 0 to 60. We express it like this. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. And now we can begin to answer questions on the probability of a particular event occurring. PDF, a little bit more language. Probability density function is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. This will make more sense in a moment when we start to draw and actually do a problem together right about now. Okay, so the graph below illustrates properties for the time, the one we were looking at for the parcel service. So let me sketch this for you here. Let's suppose, I like to suppose you didn't see that. Let me blank that out. So we know that from 0, x can range from 0 to 60, okay? Note the area of the rectangle is 1. So when you're dealing with the PDF function, the total area under the curve, or in this case, it's a rectangle, is 1. And the graph is greater than or equal to 0 for all x between 0 and 60 inclusive. This is what a lot of people say, oh, so the uniform density function looks like a rectangle. Yes. Because now what I want to ask, though, and I'm going to do this in a different color, suppose you were trying to draw this on your own, right, and you didn't know the height of the rectangle. So I'm just going to put question mark here. If this is from 0 to 60, the x ranges from 0 to 60, and you know the total area of the rectangle is 1, what do you know about rectangles? You know area equals length times width, right? So you might want to know, what's the width of this rectangle? Well, if the area equals 1, and the length from here to here is 60, then I'm just going to write a star here. 60 times what makes 1? Well, just like in algebra, you would divide by 60, solve, you got 1/60. So now when I erase this, I'm going to erase this here, see? That's how we know that's how we know that the height of the rectangle is 1/60th. So if you're drawing it on your own, you have to think about what x ranges from 0 to 60, and then think about what the height of your rectangle is going to be, knowing that the area needs to be 1. Okay, that's phase 1, is to draw it. Now let's answer a question regarding probability. Values of the random variable x less than 0 or greater than 60 are impossible. Thus, the function value must be 0 for x less than 0 or greater than 60. Okay? So that's just a fancy way of saying we're only looking from here to here on the domain from 0 to 60. The area under the graph of the density function over an interval represents the probability of observing a value of the random variable in the interval. We really just want to get you used to associating area under a curve with probability that a particular event occurs. Okay, here we go. This is the one I was waiting for. Okay, so the probability of choosing a time that is between 15 and 30 minutes after the hour is the area under the uniform density function. So that's like saying, what's the probability this package is going to arrive from 10, because remember it went from 0 to 60, anywhere between 10 a.m. and 11 a.m. So this is like saying, what's the probability it arrives between 10:15 and 10:30? Well, now we know we're looking for this area right here. Okay, and then just think about geometry, really. What's the distance from here to here? 5 units. From 15 to 30, right? So the area of that blue rectangle there, it's good old length times width. Well, from 15 to 30, that's 5 units. And the width, or more as the height in this picture, but the width we know is 1/60th. So whatever 5 times 1/60th is, which is I just realized I misspoke there. The distance from 15 to 30, whoops, elementary math. I was looking at it like, why am I not getting the answer I've written there? The distance from 15 to 30, you might be listening to me like I'm crazy, is 15 units. So that should have been 15. So you're really just, if I can say this in an easy way, when you're computing probability on a uniform density function, you're really just finding the area of the rectangle of interest. So from 15 to 30, that's 15 units. And then the distance from here to here, all the way here, is 1/60th. So whatever 15 times 1/60th is, which is written right up here, is 15/60th, which is 0.25. So that means we're going to associate that with a 25% chance that it arrives, that the package arrives from 10:15 to 10:30. Okay, objective 2, graph a normal curve. So much time in a first-year stats class is spent on the normal curve. Some of you know this as the bell-shaped curve or the Gaussian curve, because so many things are normally distributed. Heights, weights, SAT scores, GRE scores, test scores, pressure, volume, density, heritable characteristics. So many things are normally distributed, so we spend a lot of time on that. Relative frequency histograms, which would be the discrete case that are symmetric and bell-shaped, are said to have the shape of a normal curve. Properties, we want to be comfortable with the properties of a normal curve. If a continuous random variable, such as height, weight, density, pressure, volume, those are all continuous random variables. If it has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve. And now what we mean by that, without going too deep into the calculus, the curve has an inflection point at mu minus 1 sigma and an inflection point. Inflection point means where it changes concavity from concave down to concave up. Okay? So basically has inflection points at mu minus 1 sigma, mu plus 1 sigma. You'll also notice that the tails approach the x-axis and never touch. That's called asymptotic to the x-axis. I also wanted to mention that, there exists a whole family, I'm going to write here, a whole family of normal curves, all with their own mu and all with their own sigma. And a lot of people say, how does sigma affect things? Well, here, notice this pink one here is drawn. It's centered at 0. It has a mean of 0. It has a standard deviation of 1. Notice this blue one has a mean of 3, also has a standard deviation of 1. So notice their shapes are like exactly the same. However, notice down here, the pink one has a standard deviation of 1, and the blue one has a standard deviation of 2. Well, what happened? Well, notice the pink one is more densely packed around the mean. So they're both centered at 0. Both of the curves, the blue and the pink one, are centered at 0, but the blue one's more spread out, more squat and spread out. It makes sense because its standard deviation is higher. So the lower the standard deviation, the closer to 0, that you're going to have, it's still going to be a normal curve, but it's going to be skinny and sort of densely packed around the mean. Okay? Gauss, we're going to show the Gaussian formula for the normal distribution here in a moment. It's amazing to think that he was thinking about this in the late 1700s, before the graphing calculator. Okay, here we go. State the properties of the normal curve. This is what I wanted to say. So I've begun writing this function, y equals, how in algebra you sketch y equals x squared and you see a parabola. Well, imagine Gauss, he says, all right, I'm going to sketch this. Look at this lovely thing. Okay? 1 over sigma root 2 pi e to the negative 1/2 x minus mu over sigma whole thing squared. What Gauss said was, gee, this will draw a normal curve. Any normal curve, as long as you know sigma and as long as you know mu, the mean, it'll sketch any normal curve. And it's mind-blowing. And with what properties? What are the properties? Well, now we know it's going to be asymptotic to the x-axis, symmetric about the mean, bell shape, total area under the curve is 1. But the thing is, there's an infinite supply of normal curves, all with their own mean and all with their own sigma. So Gauss decided to standardize. And I just want to write that on here. I'm going to do this in a different color. If you so I'm just going to write here Gauss, give him some credit, my favorite mathematician. If you let sigma equal 1 and mu equal 0, then you're no longer looking at just any old normal curve. You're looking at the standard normal curve, which is the one you have in the back of your book, in your stats book, which we're going to be very familiar with in a second. Okay? So it is symmetric about the mean, mu. The mean, the median, the mode are, all at the same point, single peak. And it's centered about mu. Has inflection points, as we know, at mu plus or minus 1 sigma. Total area under the curve has to be 1. So Gauss is saying, he created the function that has all these properties. And the area under the curve to the right equals the area under the curve to the left. So it's symmetric, which will be a half on either side of mu. As x increases without bound, the graph approaches but never crosses the horizontal axis. That's called an asymptote. And the empirical rule should apply, that 68% of the area under the normal curve is between plus or minus 1 sigma, 95% is between plus or minus 2 sigma, etc. So now, before you took the empirical rule for granted, now let's play with something here. I'm actually going to type in that lovely formula that I just showed you, standardize the Gaussian distribution with sigma equal 1 and mu equal 0. I'll type it into the TI. Okay, now I'll show you what I did here. Remember when we said the Gaussian, the 1 over sigma root 2 pi e to the negative. And this is something you can do without even having a lot of calculus under your belt or anything like that, just basic algebra. Just go ahead, and let sigma equal 1 and mu equal 0 standardize. Well, that's going to simplify the algebra a lot, because think about it. If sigma equals 1, you can almost just 1 times anything is itself, so you just have 1 over root 2 pi. And then you'll see what I typed into the calculator here, 1 over root 2 pi. And then this will simplify a lot. If sigma equals 1 and if mu equals 0, you're just going to have x squared in there. So you'll just end up with e to the negative 1/2 x squared. So basically I typed in that version into the calculator, and just think about Gauss. Before the graphing calculator knew that that would sketch the standard normal curve. Well, let's see if he was right. Now what I will say is I went into window and I sketched it from -4 to 4, which would be like plus or minus 4 standard deviations. Y min and Y max. You can see my scaling. And I won't make you replicate this drawing, but I think it's cool to take a look at this. So there we go. We've got our curve. He knew that's what it would look like. So we've got our curve with all those properties we said. And then, I know this is not a calculus-based course, but imagine, now you'll know where this rule came from. In calculus, you integrate a function. You perform integration. We can do that lightly on here. We'll integrate the function. Integrate gets associated with area under the curve. So we integrate the curve, and I always tell everybody, look, you're doing calculus, even if you never had calculus before in your life. So integrate the curve from -1, or integrate the function from -1 to 1, which basically means, hey, what's the area under the curve for plus or minus 1 sigma? Well, now you know it better spit out 68%. Look at that. Shades it. I'll make it larger so you can see it. 68%. And you can imagine if I integrated the function from -2 to 2, that'd be 95%. Okay, so that's just an illustration of where that rule came from. Okay, objective 4, explain the role of area in the normal density function. The data on the next slide represents the heights of a random sample of 50 two-year-old males. So you've got 2-year-old males, and there's 50 of them. Draw a histogram of the data using, lower class limit of 31.5 and a class width of 1. Then it says, do you think the variable height of the 2-year-old males is normally distributed? Well, here's the data, and I'm not going to make you put that in the graphing calculator, but just think about if you had to. Okay, you could produce a histogram, you know how to do that, and now you see the data is fairly normally distributed, bell-shaped, so the heights are normally distributed. Then on the next slide, we're going to have a normal density curve drawn over the histogram, and we want to see, how does the area of the rectangle corresponding to a height between such and such a bounds relate to the area under the curve between those heights? Okay? Well, I mean, just visually. So we can see, if I color this whole rectangle, whatever that physical area is, it's going to be ever so slightly more than the area under the curve to those bounds. But actually, let me color that different. If you look closely, if I shade in under the curve, see, you're also getting a little bit of area there too. If I shade the area under the curve now in green, so the area under the curve from 34.5, to 35.5 is very close, to the area of the rectangle from those bounds. So what we're getting at is the smooth continuous curve is a good approximation. Okay, area under a normal curve. Suppose that a random variable x is normally distributed with mean, mu, and standard dev sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the interval of values, so you could interpret it as that, or the probability that a randomly selected individual from the population will have that characteristic. So we can interpret that either way. All right, let's practice. We're going to draw a normal curve with the parameters. Here we're looking at weights of giraffes, normally distributed with mean 2200, standard dev 200. So you just want to practice kind of sketching a normal curve. It's not the perfect sketch there, but centered at 2200. And then I always write the standard deviation off to the side. Standard dev 200. Okay? Shade the area under the normal curve to the left of 2100. Now this is nothing fancy. We know that 2100 lives to the left here. So 2100. And it says shade the area to the left of that. So nothing fancy. Now it says suppose that the area under the normal curve to the left of 2100, suppose we find it's 0.3085, this area, this red area. Provide two interpretations of the results. Well, that's like a 31% chance of randomly selecting a giraffe with a weight less than that. So one interpretation is, the probability of a randomly selected giraffe that weighs less than 2100 is 31%. And the other is that the proportion of giraffes who weigh less than 2100 pounds is also 31%. So we can interpret, I just really want to get you exposed to the fact that we can interpret that probability, that decimal, 0.3085, with either one of those sentences. Okay, depending on the situation at hand. All right, so I don't want this podcast to go too much over 21 minutes, so I'll probably break it into another one because we have to figure out, yes, I will. In section 7.2, we're basically going to figure out how to use that Z table in the back of our book and how to use our graphing calculator. All right, see you on the next one.